sorry. So you're given a problem where a cannon, where a cannon fires a cannonball at muzzle velocity of 40 meters per second.
You did have to.
Would you rather make it 400 meters per second? Okay. 400 meters per second. That's pretty fast, right? That's still slow. I mean, that's like a quarter of a mile in a second. That's still a little bit slow. Okay. Low power cannon. We don't want to hurt it, right?
Yeah.
All right, so I can make it 4,000 meters per second, but then all of a sudden we're supersonic.
Yeah.
I think things get a little squirrely. All right, so common problem. Here's a velocity at an angle. And 30 degrees is a very common angle that you'll see here very shortly. And the question might be, what is the horizontal range? And so horizontally, I'm looking for my distance. And maybe that's all they give me. You've got a muzzle velocity and an angle, and I'm looking for the horizontal range.
It's going to be about 13,856.
Okay, I haven't worked this out. I was just going to show you common technique for this 400 meters per second. Some of that is vertical, right? Because it's going to gain velocity.
Yeah.
It's not shot straight up. It's not shot perfectly horizontally like the previous problem. So some component of that 400 meters per second, if I want to break that into its horizontal and its vertical components, really what I'm looking for are what's the length of this side of the triangle. Well, that's going to be my initial vertical velocity. And what's the length of this side of the triangle? That's going to be my horizontal rate. So I have a 30-degree angle. This is a 30, 60, 90 triangle. The length of the hypotenuse is 400 meters per second, 400 newtons, 400. It doesn't really matter. It has a magnitude of 400. So we all hopefully recall our trig identities. So SOHCAHTOA, sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse. Turns out that you see this velocity and this angle, rule of thumb that I learned at one point that I teach my kids, and they can all recite it, every single time. Uncle Sam wants you to sign up for the Army. Sign. So for your initial vertical velocity, it's going to be 400 meters per second times sine of 30 degrees. Sign up. So if you use sine for your initial vertical velocity, what trig function do you think you might use for your initial horizontal velocity? Cosine. So that would be 400 meters per second times the cosine of 30 degrees. So I'm in pretty good shape now, right?
Yes.
Find horizontal distance, I still need time. So that means I'm going to come over here and find time. Well, vertically, acceleration is always negative 10 meters per second squared. Delta x, do I know how high it went? No, probably not. So, turns out delta x is usually not useful in problems like this, but my final velocity. If it had an initial vertical velocity of 400 times the sine of 30, by the way, what's the sine of 30 degrees? One of those special ones.
25?
A half, exactly. Yeah, so the initial vertical velocity would be 200 meters per second. Well, when it hits the ground, remember everything is symmetrical. So if it has an initial vertical velocity of 200 meters per second, what's its final vertical velocity going to be when it hits the ground? Negative 200. So if I know initial and final vertical velocity, acceleration, I want to find time, I can use kinematic number one, v is equal to do plus at. I could figure out how high it went. What's my vertical velocity going to be right here at the apex? 0, right, because it no longer has a positive velocity. It's going from positive to negative. So it's 0 right here. I could set my final velocity to 0 and solve for time. That's going to tell me how much time it's spent going up. Then I just multiply that by 2 to get the time that it's spent coming down. Another common question that you may see is, say right here, what is its acceleration? It's negative 10, right? Negative 10 meters per second squared. Right here, what is its acceleration? Negative 10 meters per second squared. When you list the vertical and the horizontal, oh, what's the acceleration, negative 10? Yeah, everybody gets that. But then you're thinking, oh, well, right here, its vertical velocity is 0, so it must not be accelerating. It's not a true statement. If it's in free fall, on its way up, at the apex, on its way down, acceleration is still under the influence of gravity. If I were to draw that a little bit nicer, my velocity versus time graph, it had an initial velocity. This graph is going to look just like that. Constant slope. What is the slope of this graph? Negative 10, right? It's in free fall. It's accelerating due to gravity. Right here, its velocity is instantaneously 0, but it's still accelerating. It's going from positive velocity, negative acceleration, slowing down, to now down here it has a negative velocity. It still has a negative acceleration. On the way down, it's speeding up. So I just wanted to touch on that two-dimensional motion problem, where you have an initial vertical velocity that's time 0. So same techniques still hold true. Separate the vertical from the horizontal, but now you have to take that initial velocity that's at an angle and figure out how much of it is vertical, how much of it is horizontal. Uncle Sam, sign up for the Army. Will help you hopefully not get your trig functions backwards. It's nice if it's a 45-degree angle, because then the sine of 45 degrees is equal to the cosine of 45 degrees. And by the way, that's where you get your maximum horizontal range. As your angle increases up to 45, your horizontal range gets larger and larger and larger. But beyond 45, it gets shorter and shorter and shorter until you hit 90, your horizontal range is 0. It's going to come right back down where it started. And one last question that you may see at some point is a 10-degree angle and an 80-degree angle. You're going to have the exact same horizontal range. A 20-degree and a 70-degree, same horizontal range. So complementary angles. 70-degree angle, it's going to go a whole lot higher, but it's going to cover the exact same horizontal range as a 20-degree angle. So 1 degree and 89 degrees will have the same horizontal range. All right, so next unit, dynamics, Newton's laws. Dealing with forces. Newton's first law is the law of inertia. Inertia, another word for inertia is mass. The more mass an object has, the more inertia it has. Inertia is just a measure of how much an object resists a change in its motion. If an object is not moving, it wants to continue not moving unless a net force acts on it. If an object is in motion, it wants to continue moving in a straight line at a constant velocity unless a net force acts on it. So the more mass an object has, the more inertia it has. Most of the dynamics unit will be focused on Newton's second law, which is F is equal to ma, or A is equal to F over m. The relationship between acceleration, mass, and the force applied. Very simply, a force is a push or a pull. It can be, literally you putting your hands on something and pushing it, grabbing it and pulling it, or tying a string around it and pulling it. We refer to that as tension, a tension force. Gravity is a non-contact force. Gravity operates at a distance. Or the other type that we'll run into is a normal force, which is a contact force, which plays into friction. Right now, my hands are moving. There's no friction between them. Why? They're not touching. As soon as they're touching, I have a contact force. Now there's friction. The unit for force is a Newton, which is a kilogram meter per second squared. It's mass times an acceleration. Really, the only thing that you need to worry about here that you would see is gravitational force. Electromagnetic forces, if you take AP physics at some point, you get into electrostatics and magnetic forces. But really it's, and I guess we'll touch on it later in the year in the unit on electrostatics. But for what we're doing in pure dynamics, it's going to be a push or a pull, tension in the rope, gravity, normal force, friction. The nuclear forces, I'm not going to spend any time going through those. So the first law, the law of inertia. The second law, F net is equal to ma. To me, the second law is more easily understood if you solve for acceleration. Acceleration is the net force divided by mass. So A is equal to F over m. The acceleration of an object is directly proportional to the force applied, the net force. And that makes sense. If I apply the same force, or if I apply two forces to an object, a larger force and a smaller force, the larger force is going to result in a greater acceleration. But if I keep my force constant, and I always use the example of a mouse and an elephant, if I apply the same force to a mouse and an elephant, which one is going to accelerate more? Mouse. Why? Less mass. So smaller mass, notice it's in the denominator here, it's inversely proportional, where there's an inverse relationship. Smaller mass results in greater acceleration. But obviously you can solve this for a net force is equal to mass times acceleration. So net force, key idea, free body diagrams. Hopefully that's been drilled and drilled and drilled. Free body diagrams are your friend. I can't tell you how many students I've had come to me that, Mr. Furman, I'm struggling with this problem. I'm not sure how to set it up. I'm not sure what to do. And I'll say, where's your free body diagram? They go, well, I didn't draw one. I'll say, go back and come back and redone it. And usually they'll draw the free body diagram and they'll see what their mistake was or why they were struggling. It really helps you to collect and organize your thoughts. You've got to be able to draw an accurate free body diagram. The whole problem often becomes very, very clear if you have an accurate free body diagram. Newton's third law, all forces come in pairs. And a lot of times it's referred to as, for every action there's an equal and opposite reaction. I think the more clear approach or the more clear definition is the force of object A on object B is equal and opposite to the force of object B on object A. So if I'm pushing on this wall, the force of my hand on the wall is equal and opposite to the force of the wall on my hand. I give the example of, again, taking it to an extreme, of I'm driving my car, a bug hits the windshield. What's greater, the force of my windshield on the bug or the force of the bug on the windshield? They're the same. You think, oh, well, the force on the bug is a lot greater. No, they're the same. Newton's third law. Two objects of equal mass, colliding into each other. Yeah, that makes sense, that, you know, the forces would be the same. But you take, you know, two large extreme objects, you know, the extreme differences in mass, you might think, oh, well, there's a greater force on the smaller object. Experiences a greater change in momentum when you get to momentum, but that's a different topic. Mass versus weight is a common type of question. The mass is just the amount of matter in an object. Does not change wherever you go. You're on Earth, my mass is about 100 kilograms. If I go to the moon, my mass is 100 kilograms. I will weigh differently because weight is a measure of the gravitational force. There's less gravity on the moon, less gravitational force. Weight is mass times little g, which is 10 meters per second squared on Earth. And I think it's about 1.6 meters per second squared on the moon. So you will weigh differently. Stand on a set of scales on the moon, you're going to have a different weight. Your mass does not change. So a very common question, conceptual question is, you know, you weigh 1,000 newtons on Earth, you go to the moon, what is your mass on the moon? So maybe you have to figure out what your mass is on Earth, and then it's not going to change, you know, on the moon. Frictional forces, caused by objects rubbing against each other. It's due to imperfections in the surfaces of the objects. Normal force, mathematical definition for normal is perpendicular. So a normal force is a contact force between two objects, and it is always perpendicular to the surface of contact. So if I'm standing on the ground, gravity is going to be a downward force, the normal force is upward. But if I'm standing on the side of the hill, gravity still is going to be a downward force, but normal force is going to be perpendicular to the hill. Again, the only non-contact force that you're interested in for this type of problem is going to be gravity. Friction. You've got two types of friction. You got static friction and kinetic. Static friction is a less than or equal to relationship. So say, for example, I've got the stapler on the desk. It's not moving. Right now, there's no frictional force. Gravity is pulling down. There's a normal force in the upward direction. But what if I push on this stapler with half a newton? Is it accelerating? It's not moving. So if I'm exerting a force in that direction, it didn't accelerate. That means that friction has to be exerting the force in this direction. So if I apply a half newton, static friction is exerting a half newton. Maybe I push a little bit harder. Now I'm applying 1 newton of force. Is it accelerating in that direction? It's still not accelerating. So now static friction, before it was a half newton, it basically only provided enough force to counteract the force that I applied. I applied 1 newton, it's exerting 1 newton back. Maybe 1.5 newtons, 1.5 newtons of static friction. At a certain point though, I can push on this thing and it starts to move. So I can exceed that static friction force. Then you go into sliding friction or kinetic friction. Static friction is always going to be greater than kinetic friction. It takes more force to get something to start moving than it does to keep it moving. If you look at the microscopic surface, if something is not moving, the imperfections on the surface are going to be arranged something like this. But once it starts moving, there's actually a little cushion of air between it, And it's easier to keep it moving because of that cushion of air than to let it stop, because once it stops, then those imperfections are gonna come into place. And rolling friction, something you'll get into more when it comes to rotational motion, which is usually a second semester. I covered that in Unit 7, I think, out of 10. In general, the frictional force, we said you have to be in contact for there to be friction, and that contact force is the normal force. So frictional force is equal to mu Fn. Mu is the coefficient of friction, and you have two different mu values for any two surfaces. You have mu s, mu static, and mu k, mu kinetic. So it depends on when you're looking, and a lot of times the problem will provide you both of these mu values, and you have to determine, is this object moving? If so, I use the coefficient of kinetic friction, or maybe this object is not yet moving, I'll use static friction. So that's and generally the problems will provide you both of those just to test and see if you understand what type of friction is in place. I refer to friction as an equal opportunity force. It always acts in the direction opposite the applied force. So if something is sliding in this direction, friction is exerting a counteracting force. If I then stop it and I pull it in this direction, friction is going to exert in the opposite direction. So whatever the direction of motion is, friction is going to be in the opposite direction. So notice here, this shows the static friction. That's that less than or equal to relationship that I mentioned. Kinetic friction, once it is sliding, then it's an equal relationship. So determining whether something is sliding or not, you have to determine, is enough force being applied to overcome static friction? If it's not, then you're dealing with static friction. If it is, then roll over and use kinetic friction. Very common free body diagram. An object on a ramp. You've got three forces acting on it. You've got a normal force, perpendicular. You've got gravity acting down, and then you've got friction. If it's sliding down the ramp, friction is going to be up the ramp. Notice that not all of these force vectors are parallel or perpendicular to each other. The problem with a ramp, typically what you want to do is rotate your coordinate system such that it's parallel to, which notice friction is already parallel, or perpendicular to, your normal force is perpendicular. The only force that you have that's not either one of those in an example like this is gravity. Gravity is straight down. Remember when I said Uncle Sam wants you to do what? Sign up. When you have an object sitting on a ramp with the angle theta, why does it want to slide down the hill? Gravity, right? So slide down the hill, sign down the hill. Which trig function do you use for gravity down the hill? Sine. So that's mg sine theta. So then the gravitational force onto the ramp is going to be mg cosine theta, which if there are no other forces, you know the normal force is going to be mg cosine theta as well. Which is helpful because the frictional force is going to be mu Fn, and if you know the normal force, frictional force is going to be mu mg cosine theta. Again, unless there's another force acting on it. It's possible that you have a rope tied to it pulling at an angle, maybe some other forces that you would have to resolve at that point. Net force, big idea. Net force causes motion. Net force is something you will calculate or derive directly from your free body diagram. Draw a free body diagram. You got to get accustomed to that. Once you draw a free body diagram, in a simple case, all of your forces are going to be parallel or perpendicular. So an object on the flat ground, you're pushing somebody along in a wagon, you're pulling somebody on a sled. If all the forces are perpendicular or parallel, it becomes very easy. Just like with projectile motion, you can separate your vertical from the horizontal. If you have forces at an angle, then you got to break them into their components, their vertical and horizontal components. To sign up for the Army thing, just like for kinematics, works for force vectors as well. As long as that angle is the angle between the horizontal and the vertical, sign up, you might work just fine. So you'll see this sigma character. Sigma F, that just means the sum of the forces, and you can sum the forces in the x direction and the y direction. You can treat those two problems in that way. It might be accelerating just in the x direction, it might be accelerating just in the y direction, or possibly accelerating in both. So the type on here is kind of small, but free body diagrams, can't stress enough how important those are. Once you draw your free body diagrams, then you can start applying the sum of the forces to solve for acceleration. Common problem, very, very common problem is an equilibrium problem. If you read a problem and it says something about an object is either at rest or moving at a constant velocity, immediately those two terms should trigger bells going off in your head. Constant velocity or at rest. We're going back to Newton's first law. An object at rest will remain at rest unless it's acted on by a net external force. Well, if there's no net external force, it's going to remain at rest. That doesn't mean that there are no forces acting on it. What it means, though, is that those forces are in equilibrium. Just like right now. I'm standing here. I'm not accelerating. Two forces acting on me. Gravity, normal force. They're equal in magnitude, opposite in direction. Maybe somebody pushes on me from this side and somebody else is pushing on me from this side. If I'm not accelerating, that means the magnitude of those two horizontal forces are going to be the same. So if you see at rest or constant velocity, you can immediately jump to two very, very useful, helpful conclusions. U equals D, L equals R. Any idea what those mean? U stands for up. Up equals down, left equals right. So if you see a problem that says an object is at rest, you can immediately jump to the conclusion that my up forces are equal to my down forces. You can set those equal to each other. And I would encourage you on, say, a free response question, write literally up equals down, because there's probably a rubric point that says, 1 point, if the student gives an indication that they recognize that the up forces are equal to the down forces, or that the forces are at equilibrium, or that the net force is 0. Up equals down, the net force is 0. Well, L equal R, what's that? Left equals right. So if you take all your forces from your free body diagram, We immediately can say up equals down, left equals right, and that's a pretty straightforward problem to solve. But what if you don't have up equals down and or left equals right? I'm not sure if I really want to raise it all the way or just resting your head on it. If the forces are not balanced, then you get into an object being accelerated, or being accelerated. I applied 10 newtons of force in that direction, but friction is only providing 2 newtons of force in this direction. The force is not balanced. Net force in that direction is 8 newtons. If I'm pushing something at a constant velocity, my push in that direction equals, what's the opposing force? Friction. So if I'm pushing with 10 newtons in this direction at a constant velocity, I know immediately that the frictional force is 10 newtons. Even if I don't know mu, or if I don't know Fn, if the question is, you're pushing an object with 10 newtons at a constant velocity, what's the frictional force? 10 newtons. Left equals right. Simple as that. If you were asked on a free response question to draw a free body diagram, and say there is a force being applied at an angle. This is what it might look like. Say you have gravity, you've got a normal force, you've got some frictional force, and maybe you've got, tension. You're pulling a box on a string. This is what your free body diagram would look like. Actually, gravity should be a little bit shorter because the length of your arrow indicates the magnitude of the force. So, actually, it would be longer, if I'm not mistaken, because this tension has an upward force as well. So, even though to solve the problem, you might want to take this tension and break it into its components, how much of it is horizontal and how much of it is vertical. If you're asked to draw a free body diagram, do not break them into their components. You may need to do that to solve the problem. You can come over here, off to the side and solve the problem. You might end up with, you have some normal force, some component of tension, some component of tension, gravity, and frictional force out to the left. So if you say up equals down, this force plus that force equals that force, and whatever your acceleration you're pulling it, probably a little bit greater force on that side. So true free body diagram here, maybe what you need to do to solve the problem.